Are you 12? This is the topic of vectors for the International Baccalaureate course Analysis and Approaches. In this video, we're going to look at constant velocity problems. So let's start with some real-life applications of vectors. Minnie can swim at a rate of 1.6 meters per second, and a river flows at a rate of 0.6 meters per second. What is her speed if she swims with the current? Now, the best way to do these questions is to draw a diagram. Here's Minnie's rate that she swims at, and here's the river. And because they're both in the same direction, we can add those two vectors together, and so her speed is 2.2 meters per second. What if she swims against the current? So again, here we've got Minnie's rate of swimming, but this time the current goes the opposite direction. So we're going to do 1.6 take away 0.6, so her speed is 1.0 meters per second. Now let's make it a little bit more complicated. This time she wants to swim across the river, which is a distance of 60 meters. How will her speed and direction be affected? So again, we draw a diagram. Here you can see her rate of swimming here and the flow of the river. Now obviously she's going to be pushed downstream. So we're just going to use Pythagoras' theorem to work out the speed that she will be swimming at. And it is 1.71 meters per second. So we know the speed, but we also need to know the direction. And it's just a matter of working out this angle. It's just tan. So tan theta is equal to 0.6 on 1.6. So theta is 20.6 degrees. We can also be asked where she will end up. So in this case, I'm not interested in the rates. I'm interested in this distance. So 60 meters here, x is what we want to find out, and we just calculated that this angle was 20.6. So just using simple trigonometry, x is equal to 22.6 meters. Now let's calculate how long the swim will take. So we're going to use Pythagoras' theorem. These are both distances, so that's going to work out the distance that she actually swims, which is 64.1 meters. Now, we also know the speeds, because we just calculated this. So she's swimming at a rate of 1.71 meters per second because of the current. So we can just use time is equal to distance divided by speed, and it's going to take her 37.5 seconds. Here's another really common question. How should Minnie adjust her swim in order to end up directly across the river? So instead of swimming straight across and then ending up downstream, she's going to swim at an angle upstream and then with the flow of the river end up directly across. So we know she swims at a rate of 1.6 meters per second, and here is the river flow rate. So we want to work out this angle. This time it is sine. And so she needs to swim 22.02 degrees upstream. Now let's try another example. An aeroplane is flying in a northeasterly direction at 600 kilometers an hour when a southerly wind blows at 36 kilometers an hour, pushing the plane off course. Part A, draw a vector diagram for this scenario. So you can see we have this vector here, it's a plane, and then here is the wind. And we just need to add those two together, and the resulting vector is the path of the plane. Part B, where will the plane be after 20 minutes? So we want to use cosine rule to work out the length here of this vector, and that will be the speed. So we know that's 135 degrees. So cosine rule, I've used S here for speed. S squared is 36 squared plus 600 squared minus 2 times 36 times 600 cos 135. So the speed is 625.97 kilometers per hour. We want to know after 20 minutes where the plane will be, so I'm just going to divide that by 3. So the distance travelled is 209 kilometers. We also want to know the direction of the plane after 20 minutes. So let's work out this angle here. sine theta over 36 is equal to sine 135 over 625.97. And so theta is 2.33 degrees. So the new direction is 45 degrees plus 2.33 degrees, so 47.3 degrees. C, in which direction should the pilot head in order to keep his charted course? Now, we're going to fly in roughly this direction so that when the wind pushes north, we're going to end up flying along here. So we want to work out that angle there. That's pretty tricky. We know that this angle is 45 degrees, but there's not quite enough to use the sine rule. So we're actually going to work out the speed along here first using the cosine rule. And the speed will be 575.1 kilometers per hour. And now using the sine rule, we have sine theta over 36 is equal to sine 45 over 575.1. And so theta is 2.54 degrees. The pilot should adjust by 2.54 degrees. Okay, let's move on to constant velocity problems. Now, we've seen the vector equation of a line before. It involves a point that lies on the line, a parameter, and a direction vector. And we can use this vector equation to represent the path of an object. A1, A2 will be the initial position because the parameter t represents time. And the vector B1, B2 is the velocity vector. So let's write the vector equation for the path of an object with initial position 1, 3 and velocity vector 4i minus 2j. And this is really easy, isn't it? It's just vector xy is equal to the vector 1, 3 plus t multiplied by the vector 4, negative 2. If distance is in meters and time is in seconds, where is the object after 5 seconds? All we do is substitute the 5 in here. So the position will be 21, negative 7. Now let's calculate the speed of the object. So that's going to be the square root of 4 squared plus negative 2 all squared, which is root 20 or 2 root 5 meters per second. Let's work out when the object is due east of the origin. Now, again, let's draw a diagram. So we know it looks something like this. It starts at 1, 3, and then this is the velocity vector. So every second it goes 4 to the right and down 2. So it's roughly like this. If we want due east of the origin, well, that's the x-intercept. And the x-intercept occurs when y is equal to 0. So let's solve this here. 0 equals 3 minus 2t. T is equal to 1.5 seconds. Now we might be in a situation where we need to find the velocity vector. And we can do that easily from the direction vector. Recall that vectors are parallel if they are scalar multiples of one another. And here's the thing, the only difference between the velocity vector and the direction vector is magnitude. So to form the velocity vector, we take our direction vector, divide by its magnitude, and multiply by the speed. And this is really useful because the velocity vector tells us how far the object moves in each direction in 1 unit of time. Let's look at this example. A model aeroplane flies directly from point A towards point B with a speed of 6 meters per second. What is the position of the aeroplane after 5 seconds? So we are going to start by forming the direction vector AB. And now we're going to form the velocity vector. Firstly, we're going to divide by the magnitude of AB and then multiply by the speed. And so the velocity vector, how far the object moves in one time unit, in this case 1 second, is negative 4i plus 2j minus 4k. So now that we have our velocity vector, we can find our vector equation, which is this. R is equal to the vector 1, 1, 2 plus t multiplied by the vector negative 4, 2, negative 4. If we want the position after 5 seconds, we just put t is equal to 5. So after 5 seconds, the model aeroplane has coordinates negative 19, 11, negative 18. Okay, let's finish off with a past exam question. Two ships A and B are observed from an origin O. Relative to O, their position vectors at time t, hours after midday, are given by RA and RB, where distances are measured in kilometres. Find the minimum distance between the two ships. So we're just going to take our generic points, 4 plus 5t, 3 plus 8t, 7 plus 0t, and negative 3 plus 12t, and form the vector AB. I'm tidying that up, and we want the length of that vector. Now this, of course, is the distance between the two ships at any point in time. And so tidying it up, we have the distance is equal to the square root of 41t squared minus 78t plus 45. If we want the minimum distance, we're going to differentiate this and put it equal to 0. So remember, this is 41t squared minus 78t plus 45 all to the power of a half. So the derivative is a half multiplied by 41t squared minus 78t plus 45 to the power of negative half times by the derivative of that inside function. And when I solve this equal to 0, this part here is all in the denominator, so it doesn't really matter. We only need to solve 82t minus 78 is equal to 0. So t is equal to 0.9512 hours. And then our final step is to substitute that into our equation for the distance. And so the minimum distance between the two ships is 2.81 metres. Okay, that's it. Our next lesson is our final lesson for vectors, and it's on geometric proof.